if we think about what we need to do to show polygons congruent, there's, if I've got four-sided figure, and essentially to show two four-sided figures similar, I need to show 8 things, right? I need to show 4 congruencies of angles and 4 ratios of sides, okay? If I have 5 sides to my figure, I need to show essentially 10 things to be true. 5 angle congruencies and 5 ratios, okay? And those ratios need to be proportional. So if I'm dealing with triangles, it needs to be 3 angles congruent to 3 angles and 3 sides proportional to 3 sides, okay? Which that can be, it's a total of 6 things. It could be problematic. It can be time-consuming. It could be maybe impossible based off the information that's provided. What we have are some postulates that allow the similarity to exist without having to look at all 6 things. Much like we dealt with congruency. Okay, show 2 triangles congruent. The first thing we learn is that we got to show 6 things congruent. 3 pairs of corresponding angles congruent and 3 pairs of corresponding sides congruent. But then we spent a lot of time kind of saying, okay, we've got some postulates and theorems that allow us to cut our work in half. The same approach here. We've got some things that say you don't necessarily need to show all 6 things. 4 triangles to be similar. Okay, but you do need to show some things in particular orders. Okay, so that's kind of what we're going to talk about as we try to prove triangles similar. And the first one is a postulate, so we cannot prove it. Right? Cameron, that's what postulates mean. Okay, it means we have to take it for granted. We can show some pictures. We can do some work that way, but there is not a proof for this postulate. And what it says is if you have 2 angles of one triangle congruent to 2 angles of another triangle, then the triangles are similar. You don't have to deal with any proportions there to determine similarity. We don't have to deal with the third angle, which we should know to be congruent anyways. Okay, you only need 2 angles congruent to 2 angles, and then that is enough to say that your 2 triangles are going to be similar to one another. All right. Now the reason we don't have to talk about the third angles is because of the third angles theorem that we talked about back in chapter 2 or 3. I said if 2 angles of one triangle are congruent to 2 angles of another triangle, so let's say we eat up 100 degrees for P and Q added together, then T and S are going to be 100 degrees, right? Added together. So what do you have left over for R? 80. What do you have left over for U? 80. So that's the third angle theorem. 80 is equal to 80, so R is congruent to U, right? So sometimes you might see people write it that way, or textbooks write it as the angle similarity postulate. Our textbook thinks that's redundant because you got angle, you automatically have angle, right? So they're trying to save some writing there. Just know that if you, for any reason, they ever say angle, it's the same thing as angle. So you might see from textbook to textbook when I pull questions out of Math Excel. I'm not 100% sure what the other textbook calls this, angle, or just angle. Is that right? So what that means to us, the conclusion is that the 2 triangles are similar, but with congruencies, remember when we showed things congruent, there was something that came directly from that, and it basically, when the 2 triangles were congruent, the other sets of parts that we hadn't talked about were also congruent by CP, CTC, right? Okay. Well, what have we not talked about? With similarity, we have angle congruencies and we have proportions of side lengths, don't we? Or ratios of side lengths that are in proportion to one another. And we haven't talked about any of that here. So a direct conclusion from this, and being able to say that triangle PQR is similar to triangle TSU, is that we get PQ divided by TS to be the same thing as QR divided by SU to be the exact same thing as PR divided by TU. Okay? So that's the result from showing 2 triangles similar through angle, is that we end up with these 3 ratios that should be equal to one another. Is that all right? Okay. That's going to eventually allow us to find some missing values and a lot of the problems that we're going to deal with. You've heard me say it before. I'm going to say it again, though. We're going to go on to a lot of things in this course that are developed and proven through the use of similarity. We're going to talk about altitudes of right triangles. We're going to talk about sine, cosine, and tangent on your calculators and what those things all do for us. But they exist because of similarity. And if you have an understanding of similarity and why two figures could be similar, why two triangles might be similar, when you get stuck in those other sections and those other chapters on a particular problem, if you have the understanding of similarity, it might allow you to get yourself unstuck. It might allow you to shed light on the algebras you need to use to get to the variable that you're trying to solve for. If you don't understand similarity, you might be able to muddle through sine, cosine, and tangent, just relying solely basically on your calculator. But if you do get stuck, how do you get yourself unstuck? If you don't understand where the values come from, what the ratios and proportions mean to us, and that kind of stuff. So that's why I spend a lot of time trying to get us to realize these relationships, these ratios. Okay. This question, when we look at it, this question can get people in trouble because of what you want to do with this one and the fact that it works with this one. And then people want to try to just convert that over to every single question. If I look at this, we've got two angles congruent to two angles, right? Okay, so we do have angle-angle similarity here. But now what we have to do is we have to identify a name for this triangle and identify a name for that triangle, just like we did with congruencies. So name this triangle. What do you want to call that one? Okay, DEF is fine. So if we named it DEF, that means that the first letter over here has to be congruent to D, right? So it's going to be A. And then E needs to be B, and then C, right? We need to set that statement up because the corresponding parts, D and A should be congruent, E and B should be congruent, F and C should be congruent, right? If you don't do that, you're going to, especially on the next question and the one I think maybe after that, you're going to make mistakes because you could, without that similarity statement in this question, say, I'm just going to compare the upper right segments, 3 and 15, okay, through ratio, and I'm going to compare X and 45, the bottom segments, and I'm going to get the right answer. Does that make sense? But that's just coincidence because those two shapes are kind of just a translation of one another. Okay? Obviously, they've been dilated, they've been changed size or whatever. But the one on the left, I could just kind of drag it to the right, and they kind of match up, right? Does that make sense? Okay? Slight rotation, but nothing really too bad. But if you want to do that, or if you do that, I said do. If you do, I'm going to do it again. If you do that, be cautious because what would happen is if angle E was congruent to A, okay, and now I try to compare right to right and bottom to bottom, I run into an issue doing that. Does that make sense? Okay. I like this. This is always going to get you the right answer, okay? And it takes about 30 seconds to write all this down, so it's not really time consuming. If we can write that down, we should then know DE compares to AB, EF compares to BC, and DF compares to AC, right? That's the conclusion from saying the two triangles similar through AA. Now you know exactly what needs to be compared. There's no question about, does 3 go to 15 or does 3 go to 45? Does X go to 15 or does X go to 45? If you can substitute DE, obviously DE is the X, AB is 45, EF is 3, BC is 15, and then these two things I don't know, so I'm just going to leave them alone. And now I have the right components compared together, right? In the event, because you will see these at times, you will see that you do know values for DF and AC. And whether they're variable, algebraic, or they're numerical, we'll then shed light on maybe what you can kind of compare, what you can use to solve for X. But this one, I have to use those first two ratios. All right, now I'm a person, and I think a lot of us can probably do this. Save yourself a little bit of time, especially when the numbers get a lot bigger. You know, a lot of you can take, 15x, and then 45 times 3 is 135, right? Now, to solve and divide by 15, 135 divided by 15, a lot of you are probably going to grab your calculator, right? Let's do it this way. 15 times x is 15x, right? It's 45 times 3. It's 135, but can I write it this way? 45 times 3 that way. And now if I divide by 15, come over here and divide by 15. What's 45 divided by 15? That's 3, right? So what's 3 times 3? That was reduced to 3. 3 times 3 is 9. So that's what 135 divided by 15 would have been. Does that make sense, everyone? I think that's kind of maybe mental math algebra that you guys can use to work through things a lot faster. Well, I know what x is 9, so now how can I check myself? If I put 9 right here, okay, will this reduce to 1/5? Will this reduce to 1/5? If I'm able to reduce them in the same ratio, which ultimately means that the cross product should be the same. 135 is equal to 135, and we're good to go. Is that all right? All right, let's do another one. This one I'm just going to help you set up. I'm not going to do the math with you, or the calculations with you. We've got angle, right? All right, so if I say, let's name the first one ABC. So what do you call the second one? DEF. So we say AB to DE, BC to EF, and AC to DF. Stop me if that does not make sense. That is the number one thing that we need to know. Okay, we're taking the first two letters here, comparing to the first two letters there through division, right? Then we're moving that circle to B and C, and then move that circle to E and F to compare those. And then we compare A to C and D to F, the first and last things. All right, so we need to make sure we understand that. But now, what's AB from our picture? Just X, right? What is DE? X minus 4. BC is 5, and EF is 3. AC and DF, they're unknown again, so I don't really do anything for them. And we can cross multiply, right? Now here's a question. Is it okay to flip this x minus 4 on this 5? Yeah, but if I do that, now look what's happening. If I do that, I'm comparing those two things. Okay? And that's not what similarity tells us right now. That's a rule of proportions. But similarity for shapes tells you compare a side of triangle number 1 with a side from triangle number 2. That's where we're getting x over x minus 4 or 5 over 3. 5 comes from triangle 1, 3 comes from triangle 2. If I flip-flop those, and I get x minus 4 over 3 or something like that, then I'm looking at comparing a number from triangle 2 and a number from triangle 2. Okay? I want to go, top comes from one figure, bottom comes from another figure. Does that make sense? And that's directly what is stated with similarity of polygons. But we know once we have a proportion, we've got some rules that we're allowed to use to manipulate it so that we still develop a true proportion and still be able to solve for x. What if, now this doesn't happen this, but what if, and maybe you see the benefit of what we talked about in earlier sections, what if I would have found like maybe my ratio, don't even worry about the picture, what if I would have found the ratio to be like x over 5 compared to 3 over x minus 4? When I cross multiply there, what's your extremes going to give you? Those are your first and last ones, right? So give you x squared minus 4x, aren't they? And if you have x squared, what do you need to do? You need to factor, don't you? Okay, so that's why in 7.1, a little bit in 7.2, we saw those questions that there was no context to them, but they were just proportions, and we had to factor. Because you don't know how they're going to describe components of your pictures and how they're going to set themselves up, and you might set up a proportion from the context of your picture that gives you something squared. And what do you then do? How do you react to that? Do you just quit, or have you built the skills to address that? Hopefully we built those skills. Cameron, if I forget how to factor, what will always work? If I have x squared plus 5x plus 7, and I can't factor that, because there are no two numbers that multiply together and give me 7 after 5. What do I always turn to? Factoring does not work. Like maybe our shortcut technique. It starts with a Q. Ends with quadratic. Formula. Quadratic formula, right? Okay, so that's something to maybe commit to memory and know that maybe tomorrow when you see a question or a quiz that has you factor, if you can't use one of the shortcut techniques, or maybe on question 16 yesterday, because it was a hard, the A term, the A coefficient wasn't a non-1, okay, it was some other integer other than 1. What do you turn to? Quadratic formula will factor it, okay? So that might be your, kind of like your lifeline, and if I don't know how to do it, what can I always turn to? Quadratic formula is that thing for factoring. This question here is another AA question, but looking at the picture, there is no explicit congruencies up there, right? So we need to go through and say, okay, what are they implying to be congruent here? What angles do you know to be congruent here? Elijah? Okay, A and D. All right, why are A and D congruent? All right, so you got that line. So you look at the parallel lines, right? So those two lines are parallel. You have that guy right there, which is a transversal, correct? Okay, so essentially what we're going to, if this is AB and that's CD, we're looking there in angle A and angle D, where those angles there. And those are what types of angles? I understand when we say opposite interior, I know what you mean, but we use the word alternate. Okay, so those are alternate interior. So those are congruent, so that's good. For the same reason, would that be a transversal for the parallel lines? And would that angle be alternate interior to that one? So does that show us two angles, congruent to two angles? Okay, so that's nice, but maybe you didn't see both sets of alternate interior angles. Is it okay to say that this angle here is congruent to that angle there? Yes. Why would those be congruent? Starts with a V. Vertical, right? Okay. Or, if I'm looking at the triangle, I found the red ones to be congruent. Those are congruent by the third angle there. Okay. All right, so, just going maybe off of those. Let's name these triangles. Let's name them triangle A, maybe BE. Is that okay? If I go A, BE, what do I have to name the other one? D. Yeah, CE. Yep. Okay, so here's my reasoning for writing this out. Is because now it's kind of obvious, I think, maybe because they only give you 4 total distances. But if they would give me this distance here and this distance there, what a lot of people want to do is say, because this is the top value and that's the top value, is that they want to compare those, say top to top. They want to say bottom to bottom. Does that make sense? And you can't do that. And the reason you can't do that is this. Would you guys agree? Remember, we're talking about similarity. We're trying to match up congruent angles, right? Okay, now that triangle is going to look, I'm going to make it kind of transparent so we can move it around and see things. Can I move this triangle so it gets on top of this one so corresponding angles are congruent? Well, hopefully you recognize that to do that, I'm going to need to flip this thing, maybe up and down. Okay? Now I've got angles congruent. Top angles were congruent, right? But angle A and angle E were not congruent. A and D were the ones that were congruent, right? So now this thing needs to be flipped left and right. And now you see that the tops match, right? Now the bottom rights match, right? And those two match, right? Does that kind of make sense? Okay. And that then says if they're matched up in the same orientation, now you can say top left. So you could say, maybe I'll just put that mark there. That one will match up to that one. That side to that side. And that side to that side. You could do left to left, bottom to bottom, right to right, if the angles are corresponding. Does that make sense? But some people aren't going to do it that way. Some people are not going to be able to redraw the picture that easily and be able to put it in the same kind of orientation to one another. So what do we do? We draw this. And this effectively does that for us, okay, without us having to redraw the picture. Because this, if I know A goes to D, and I know B goes to C, it automatically gives me AB to DC. Automatically gives me BE compared to CE. And it gives me AE compared to DE. All right? And now I don't have to flip the picture multiple times or rotate it or slide it, that kind of stuff. Does that make sense? You always want to write this down. Okay? And in the past, I get people to think, I don't need that. I can visually see what's going on and what I can compare. In the coming weeks, if you do that, you're going to struggle. Okay? So get in the habit of drawing that picture. Okay? So now, what is AB? What is that distance there? It's 2, right? Okay. DC would be 5. BE, I don't know BE, right? And I don't know CE, so that one's not useful to me. But AE, x minus 1, and DE then x plus 5. So it allows you to create the correct proportion to solve for the missing parts. Right. I'll leave the algebra there, the calculations to you on that one. I believe you get maybe like 8/5 or something like that. Okay, 1.6 as your x value. And but I'm concerned about this. I'm concerned about you being able to go from the picture to this, to this, to that. And then solving for x then is just algebra. All right. Is that all right, everyone? What did we come up with for? Did you guys do it and get x? I'll do it real quick. I don't know if that 8/5 was right that I gave you. 2x plus 10, 5x minus 5, right? So it gives me 3x, 15. X is 5. I'm sorry. There's an 8/5 somewhere in one of these questions. So x is 5. Okay. So let's do this one. These questions, these are a little bit harder because of the fact that things are overlapping. You've got two triangles here. You got triangle AEB, that small one up top, right? And you got triangle ADC. And when you get questions like this, a lot of times they don't give you all the parts, and you got there's a lot of implied distances that you might need. Okay, but would you guys agree that in both triangles, angle A exists in both triangles? Okay, so I'm a person that whenever I see overlapping, I want to pull them apart. So we get AEB, and then over here would be ADC. I actually put them back together. They should give you this shape, right? There's a picture. A is in both those. That's the same exact angle in both those shapes. Now, these lines are what to one another? Parallel. So what kind of angle is that angle there compared to that angle there? Based off of the how we define them, what would that word be? They're corresponding. So that angle is congruent to that angle. So you have angle here? Do you have two angles congruent to two angles? All right, so I'm going to name this as triangle AEB, similar to triangle ADC. So then that's going to imply that AE over AD is equal to EB over DC, AB over AC. And this is where we've got to do a little bit of thought in regards to finding the missing values here. What is AE's length? Careful. Yeah, because they tell you that distance right there is 5, right? And that entire distance is 8. So I know AD is 8. So that's got to be 3, doesn't it? 5 minus 8, or 8 minus 5. So we've got AE being 3, AD is 8. EB, I don't know. EB and DC, they don't provide those. But what's AB going to be? X plus 2, right? Okay, so they're giving me AB to be that distance right there, X plus 2. Now they're saying BC is 6. So what is A to C? X plus 8. That's the one I believe you get 5 over 8 for an answer. Okay. Is that something we can do? All right. Now here's the thing. Every single time, because we're going to learn a couple more postulates here. Every single time that we use one of these similarity postulates, those are the kind of conclusions that we're going to get. We're going to try to write that similarity statement. We're going to try to write an AE over AD is equal to EB over DC is equal to AB over AC, and then plug things in and substitute, get our proportion solved. Okay. So even though we're going to learn two more properties here, two more postulates or theorems, a lot of the work is very similar to that one. And I think angle is obviously maybe the easier one to deal with. Let's come down. I'm going to skip a couple slides here. I just don't like the order I have it. I'm going to go side, side, side. Side, side, side is, I think, the second easiest similarity rule that we're going to use. Okay? And this just says if all the sides of two triangles are in proportion, then the triangles are similar. And you don't have to worry about any angle information. Okay? If all the sides are in proportion, then you don't need to worry about angle information. Right? But if all three sides are in proportion, the shapes are similar, what is the conclusion that you can draw about the angles then? If I have two similar triangles, what do you know about their angles, their corresponding angles? They have to be congruent. Okay? So that's kind of the direct link. That's the result, I guess, of side, side, side similarity. Okay. One thing you got to think about here, if I've got two triangles, let's say I got triangle, let's call this one triangle 1, and call this triangle 2. Let's just say in triangle 1, B is the smallest side length. To be proportional, to be similar shapes. Let's say this is 3 here. Let's say B is a length of 3. Okay. No matter how much bigger or smaller the triangle on the right is, okay, no matter how much I multiply 3 by, I'm going to multiply every other value up there by the same thing, right? Okay. So let's say this is, let's just throw in some random values. Let's say this is 3. Let's say that's 4. And let's say that this is 5. Now let's say I want to multiply everything by 10. I want to say that this figure here is 10 times bigger. Well, that would mean that would be 30, right? This would be 40, and this would be 50. What was the smallest side over here? 3. What's the smallest side over here? 30, right? Okay. Do you see how, if these two things are going to be similar, the smallest side always needs to compare to the smallest side, the largest to the largest, and then the middle one's going to match up? So that's all we have to check. If they give me two figures, and they want to check to see if these two figures are similar, so we'll do this top one here. They want us to see if those two shapes are similar. Now there's a question, well, what do I compare to what? Well, if they are similar, then the smallest side of the figure on the left will match up to the smallest side of the figure on the right. Because the scale factor that we use to get the figure on the right is the exact same scale factor for all three side lengths, right? Okay, I'm going to multiply 10 by the same thing to get 15. I'm going to multiply 6 by the same thing to get 9. I'm going to multiply 8 by the same thing to get 12, right? Okay. So always when doing side, which I think is maybe even might even be the easiest one, might even be the easiest similarity postulate, is to simply take the smallest side over here. What's the smallest side over here? 6. Compare that to the smallest side over here, which is 9. What's the biggest side over here? 10. Compare that to the biggest side over here, which is 15. Now it's not good enough to just to do the smallest and the biggest. You gotta do the middle ones too. So 8 and 12, right? Now we want to see if these are, to make the argument that these are similar, these all have to be true proportions. We have actually 3 proportions here, right? We got those two, we've got those two, and then we also have those two. Okay? So we have 3 proportions, but if we're creative and we understand some of our properties from previous ideas, let's just look at those two. What do I get when I cross multiply those? What's 9 times 10? 90. What's 6 times 15? 90. So that's a true proportion, right? So that means this this ratio is equal to that ratio, right? Let's look at these two. What's 10 times 12? 120. What's 15 times 8? 120. Those two are equal, right? So this proportion says those two ratios are equal. Do I have to look and do cross products of those two? No, because 6/9 is equal to 10/15, which is equal to 8/12. The transitive property says that 6/9 will automatically be the same as 8/12. What's 9 times 8? 72. What's 6 times 12? 72. But knowing the transitive property allows me to not worry about that multiplication. Okay, so it shortens a little bit of my work. Is that doable? So if that's the case, so those two things are similar. Okay, if I want to name these two triangles, let's say I name triangle UST, similar to triangle. Okay, so now I went from U to S. I went down the longest side, right? What's the longest side over here? That's 15. It's WX, right? Do I call it WX or do I call it XW though? Because here I went from U to S, so that's the longest side, and then I went down from S to T, which would have been the shortest side, right? So I need to go longest side down the shorter side, so it is WX, and then finish at V. Does that make sense to everybody? Do we understand that XWV would be comparing different parts? So now that we have that similarity statement, what's the conclusion? What can you tell me about angle U compared to angle W? They're the congruent angles. They're corresponding, right? X to X and T to V. Okay? And we're going to find out later in the chapter that T and V are what kind of angles? Anybody know? What's 6 squared? Yeah, 6 squared is 36, right? A squared is 64. A squared plus B squared should equal C squared. So 100 is equal to 100. So that's the side. But now let's talk about this one. And this one is going to be, we got a couple minutes here, so brief, but it's not all that difficult. Okay, if you understood the first two. We're going to spend several days on this stuff, so a quick introduction to this, and we'll spend more time on it later next week, or early next week. It says if an angle of one triangle is congruent to an angle of another triangle, and then the sides, including those angles, are in proportion, then the triangles are similar. So side angle side similarity means the sides that we're interested in have to sandwich the angle. Okay? Now, with congruency, the sides have to be congruent, right? We need that tag word of similarity to say that the sides in this name have to be proportional. And again, we want to go off the same idea. Smallest side compared to smallest side, largest side compared to the largest side. And if we can make that, we can see that that's a proportion. It's a true proportion. We've got the angle in between that are congruent. The triangles are similar. Which then would mean the remaining side that we know nothing about, or remaining set of sides that we know nothing about, would be the same ratio. And it would tell us the remaining angles that we know nothing about. If we correspond them, they should be congruent. So do an example of that quickly. Man, I hope that I don't go over anything in the next 5-6 minutes that you don't need to be successful in homework. Huh? You packed up already. Oh, man. All right, so do this example. It says, use the given lengths to prove that the triangles are similar. Okay, so even though it looks like it, we don't want to know anything about, that looks like it's parallel to that, right? Yep. But we don't know that. Okay, so if they were parallel, we knew that we could use angle, but we don't know that right now. But we do know that if I look at these two triangles, S, P, and Q, compare that to triangle S, R, T, which angle is reflexive there? S, yeah, that's the one that is in both figures, right? That's the one that's overlapping, it's being shared, okay? Now, what is S to P's length?
4.
4, what's SQ? 5, what's S to R?
4.
What's S to R? 16.
Oh, yeah, you're right.
Segment addition, right? What's S to T?
20.
20. Okay. We are checking, are these similar? That's a question mark there. Are they similar? Okay. Well, we've got the angle in between, right?
Yeah.
So we've got that taken care of. If they're going to be similar, we need to check the proportion of corresponding sides. So what is 4 going to relate to over here? Why? No. Not because they're both on the same line, or not because they're both the same left-hand side. It's because 4 is, of the values I know over here, it's the smallest one, right? So it's got to be compared to the smallest one that I know over here, if they're going to be proportional at all, right? Or similar at all. So 4 compares to 16. What's 5 going to compare to? 20. Okay? So, what's 16 times 5? 80. What's 4 times 20? 80. Are those two sides in proportion to one another?
Yes.
Is the angle in between congruent?
Yes.
So yes, these two triangles are similar by side angle side. Now here's my question. What's that tell you about PQ compared to RT? Let's say PQ is 3. Do you now have the ability to find RT?
Yes.
Yeah. Because this ratio is 1 to 4, right?
Yep.
So can I take this and multiply it by 4 to get 12?
Yep.
Okay. Here's another question. What's that tell you about that angle there compared to that angle there?
They're equal.
They're congruent, right? Okay. Because that's a conclusion that comes from side angle side similarity. Once you have two shapes that are similar, you know corresponding angles are congruent. Those two angles correspond. So what's that tell you about PQ and RT? They are indeed parallel. Because we had a theorem back in chapter 3 said if two lines are cut by transversal such that corresponding angles are congruent, then the lines are parallel. Okay. I'm going to open up 7-3. It's not going to be due till Tuesday. Okay. We don't have Monday.
Yep.
Not school Monday. Tomorrow we're going to quiz, so there's really no need in having to do tomorrow. Nothing on tomorrow's quiz is over 7-3. You don't need to know anything we did today. Anything new. I mean, we did some proportion and ratio stuff and understanding extremes and means. You need to know that stuff. But specifically, the new information 7-3 will not be covered.
Why are you looking at me?
Cameron, what if you were